Welcome back, dear dreamer. Tonight, we drift into the quiet path of Voyager 1, a small traveler with a patient heart and a steady kind of courage. It doesn't race through space or roar with engines. Instead, it moves with gentle certainty, gliding into the darkness as if eternity itself were simply another horizon to cross. While the world sleeps, this little spacecraft keeps going, far beyond the warmth of the sun, carrying our questions, our curiosity, and a soft echo of who we are. As you listen, let your breath loosen, let your thoughts soften, and let your mind float like dust drifting through starlight. This is not a tale of speed or noise. It is a quiet journey through resilience, wonder, and the long, peaceful patience of interstellar space. Settle in, get comfortable, and let the night open around you. If these soft voyages bring you rest, remember to subscribe and tap the like button. Now, let us begin. Voyager 1 began its quiet journey in 1977, rising through the sky on a pillar of flame before slipping into the calm of space, where the noise of Earth slowly faded behind it. Engineers and scientists watched the spacecraft vanish into the dark, not knowing that it would one day become the most distant human-made object ever created. In those early hours, its purpose was simple but profound: explore the outer planets with steady patience and send back whispers of worlds no one had ever seen this clearly before. As it drifted farther from home, its instruments woke one by one, breathing in the subtle radiation, magnetic fields, and starlight that filled the space between planets. Even then, few realized that this modest machine would continue speaking to Earth long after its designers retired, carrying human curiosity with a calm, unhurried grace. Voyager 1's mission began with Jupiter, a vast world of swirling clouds and hidden storms. Its cameras captured the planet in warm, soft colors that Earth had never seen before, revealing bands that moved like slow rivers of gas. When the spacecraft flew past, it sensed magnetic fields looping and shifting in ways scientists had only imagined. It found lightning brighter than anything on Earth, glowing deep within the cloud layers. It watched the moons, each with its own quiet personality, moving around Jupiter like dancers in a silent orbit. Io surprised everyone with active volcanoes erupting into space, a discovery that reshaped how we think about heat inside distant worlds. In those gentle moments of observation, Voyager 1 showed that our solar system was not still or cold, but alive, dynamic, and full of unexpected energy waiting to be understood. Saturn welcomed Voyager 1 with its soft rings, delicate as frost forming on a morning window. The spacecraft drifted through the planet's domain with a calm steadiness, capturing the rings in a new level of detail that astonished researchers back on Earth. Instead of smooth bands, the rings revealed tiny structures, waves, ripples, and shadows shaped by unseen forces. Moonlets hid inside the gaps, guiding ring particles like shepherds. Titan, Saturn's largest moon, appeared mysterious under its thick orange haze, refusing to show its surface even to Voyager's patient instruments. Yet that secrecy added to the wonder. Scientists realized that Titan could hold organic chemistry similar to early Earth, sparking decades of curiosity. As Voyager 1 moved past Saturn and began its escape path from the planets, the mission shifted from exploration to deep space wandering, a calm transition into the quiet outskirts of the solar system. As Voyager 1 traveled farther from the sun, the light around it softened into a gentle glow, weaker than anything familiar on Earth. Space became colder, quieter, and more delicate, filled with particles that drifted like dust in an endless night. The spacecraft's instruments continued listening to the faint hum of the solar wind, sensing how it thinned with distance. Engineers on Earth monitored every signal, knowing that the photons carrying the data had crossed many hours of empty space before reaching their antennas. The spacecraft's power, coming from its nuclear generators, slowly weakened with time, yet each system continued working with remarkable patience. In this calmer region, Voyager 1's mission became a study of boundaries, the edges where the sun's influence fades and interstellar space begins. Every measurement helped scientists understand how our star interacts with the galaxy around it, adding a gentle, steady voice to the story of cosmic winds. Traveling through the outer heliosphere, Voyager 1 observed the region where charged particles from the sun still roam, though far more quietly than near Earth. The spacecraft detected shifts in cosmic rays, tiny high-energy fragments that drifted in from distant stars. These subtle changes allowed researchers to understand how the sun creates a protective bubble around the planets, shielding them from much of the galaxy's harsher radiation. Voyager 1 acted almost like a weather station at the edge of the solar system, quietly reporting how space conditions changed day by day. Its instruments measured magnetic fields that twisted and curved in gentle patterns, shaped by the sun's slow rotation. Even though no human eyes could witness these regions directly, the spacecraft transformed them into something almost familiar. It showed that even at the very outskirts of our system, the sun's presence can still be felt, soft but steady, like a distant warmth. Voyager 1 carries the famous golden record, a peaceful message crafted for any possible beings that might one day find it drifting in the dark. This golden disk holds sounds chosen to represent Earth's gentle side: calming waves, wind brushing through trees, a mother speaking softly to her child, and music from cultures across the world. Scientists included greetings in many languages, hoping to express goodwill without knowing who might hear them. The record contains images encoded as data, scenes of mountains, animals, cities, and drawings of human anatomy. All of it was placed carefully inside a protective cover, with instructions for how to play it. Carl Sagan and his team designed the record with a hopeful spirit, imagining a distant civilization discovering it millions of years from now. Voyager 1 carries this message through interstellar space like a small, quiet ambassador of Earth's desire for connection and understanding. Voyager 1's communication system works through the Deep Space Network, a group of large radio antennas placed around the world. These antennas listen for the faintest signals, sometimes as weak as a whisper lost inside a storm, yet still detectable after traveling billions of kilometers. Every transmission from the spacecraft takes more than 20 hours to reach Earth, moving at the speed of light across empty space. Engineers interpret the data with careful patience, knowing that even small variations contain messages about the conditions Voyager 1 experiences. The spacecraft's dish antenna remains pointed toward Earth, using a set of tiny thrusters, firing brief pulses to maintain alignment. Despite its age, it continues to send back measurements with surprising reliability. Each piece of information reminds scientists that even a distant, aging machine can contribute valuable insights simply by staying calm, consistent, and connected across unimaginable distances. The cosmic rays Voyager 1 encounters in deep space tell a quiet story about the galaxy's hidden processes. These rays are fragments of atoms accelerated by ancient supernova explosions, traveling across the universe until they brush past the spacecraft's detectors. By measuring the intensity and energy of these particles, scientists learn how shock waves, magnetic fields, and winds from giant stars shape the galactic environment. Voyager 1's gentle movement through this region gives a steady record of how cosmic rays change as the spacecraft drifts farther into interstellar space. This information helps researchers understand how radiation affects planetary atmospheres, spacecraft materials, and even the potential habitability of distant worlds. Without any dramatic events, Voyager 1 simply listens to the natural rhythms of the galaxy, translating them into data that deepens our connection to the broader universe beyond the familiar glow of our sun. As the spacecraft approached the heliopause, the final boundary where the solar wind stops pushing outward, Voyager 1 sensed dramatic but gentle changes. The density of particles around it increased, suggesting that it was entering a region shaped more by the galaxy than by the sun. Magnetic fields shifted direction, revealing a subtle swirl created by forces outside our solar system. The temperature of the surrounding plasma changed in ways that confirmed predictions made decades earlier by heliophysicists. This transition marked Voyager 1's passage into true interstellar space, something no spacecraft had ever achieved. Yet the moment itself was quiet, with data arriving slowly, like waves lapping at the shore. Scientists celebrated not with loud fanfare but with calm amazement, realizing that a small machine from Earth had gently crossed into the realm between stars, carrying human curiosity deeper than ever before. Drifting through interstellar space, Voyager 1 now moves in an environment shaped by ancient stars that exploded long before the sun even formed. The gas here is thin, far thinner than any vacuum humans can create on Earth, yet filled with stories written in particles and magnetic fields. Voyager 1 measures these faint signatures with aging instruments that still perform with surprising steadiness. The data helps scientists understand how material from old stars spreads through the galaxy, eventually becoming part of new systems and planets. Even though the spacecraft no longer sees planets or moons, its journey remains scientifically rich. Each reading, no matter how small, helps build a picture of the Milky Way's structure. Voyager 1 has become less an explorer of worlds and more a quiet observer of the space between them, offering a peaceful, continuous record of life beyond the sun's fading influence. As Voyager 1 continues on its path, it moves slightly above the plane of the solar system, giving researchers a unique perspective on the shape and texture of the heliosphere. This vantage point helps scientists test ideas about whether the sun's protective bubble resembles a comet, a sphere, or something more complex. Over time, Voyager 1's slow drift allows scientists to trace subtle changes in particle flow and magnetic strength, revealing how the heliosphere interacts with the surrounding interstellar medium. This interaction shapes the radiation environment experienced by any spacecraft or potential travelers leaving the solar system. Voyager 1's measurements form a calm, steady stream of information that complements models developed on Earth. The spacecraft's long endurance has turned it into a quiet scientific instrument gliding through the galaxy, offering insight into the sun's relationship with the Milky Way in a way no other mission currently can. The power that keeps Voyager 1 alive comes from 3 radioisotope generators that convert heat from decaying plutonium into electricity. Over the decades, this electrical output has slowly decreased, requiring mission engineers to turn off instruments one by one to conserve energy. Each shutdown is handled gently, preserving the spacecraft's ability to communicate and point its antenna toward Earth. Even with reduced power, the remaining instruments continue to operate effectively, sending back valuable data. The aging generators still offer enough warmth to prevent freezing, allowing the spacecraft to function in regions colder than anything naturally found on Earth. This slow decline has been anticipated since launch, and the mission team planned carefully for every stage. Voyager 1's ability to continue working with such limited resources reflects the remarkable engineering behind it and the dedication of those who monitor it across the decades. Voyager 1 has seen more of cosmic space than any other human creation. As it moves farther away, the sun appears only as a bright star among countless others, a reminder of how small our home looks from great distances. The spacecraft's cameras are no longer active, but its earlier images, like the pale blue dot, remain symbols of perspective and humility. Scientists still reflect on that image, which showed Earth as a tiny point suspended in a sunbeam. That photograph continues inspiring discussions about unity, peace, and our shared existence on a fragile world. Voyager 1 now travels too far from the sun for solar-powered instruments, but it continues its mission in quiet persistence. Its journey offers a reminder that exploration does not need to be fast or loud. Sometimes the most meaningful discoveries come from steady observation and the gentle passage of time. Voyager 1's instruments, though built in the 1970s, remain incredibly sensitive. The plasma wave instrument, for example, detects faint vibrations in space caused by charged particles, translating them into audio-like signals that reveal the density of the surrounding medium. These subtle changes help scientists understand how interstellar space flows and shifts around the spacecraft. Magnetic field data continues to map the structure of the environment, showing how the sun's influence merges with the broader galaxy. Even after decades, the spacecraft's detectors maintain their ability to sense the smallest traces of cosmic activity. Researchers analyze these signals with great care, knowing that every reading is a message from a region humans cannot reach physically. The continued performance of these aging instruments demonstrates the durability of the mission's design and the skill of the engineers who built them to survive long beyond their intended lifetimes. While most spacecraft serve missions measured in years, Voyager 1's voyage has lasted longer than many scientific careers. New generations of researchers have taken over mission operations, each learning from those who came before. This long timeline gives the mission a sense of continuity, linking decades of scientific advancement through a single spacecraft. Students who once learned about Voyager 1 in textbooks now work directly with its data, contributing fresh perspectives while honoring the knowledge built by earlier teams. The spacecraft's steady stream of measurements forms a bridge across time, connecting scientists from different eras. This cross-generational effort shows how exploration extends beyond individual lifetimes, carried forward through collaboration and curiosity. Voyager 1 remains a symbol of how science grows, layer by layer, with each group adding insights that help shape our understanding of the universe in a calm, patient progression. The trajectory of Voyager 1 will take it near no particular star for many thousands of years, yet its path carries it gently through the general direction of the constellation Ophiuchus. Over immense timescales, the positions of stars shift, and the galaxy itself rotates, meaning Voyager 1's eventual surroundings will look very different from the familiar night sky seen from Earth. Despite its isolation, the spacecraft continues its journey with quiet determination. Its passage through interstellar space helps researchers understand the environment that exists between stars, including how gas is organized and how magnetic fields thread through the galaxy. Even though it travels alone, Voyager 1 contributes to a broader understanding of the Milky Way's structure. Its path, though simple, symbolizes humanity's desire to explore and observe, even when there is no specific destination, only the steady movement toward the unknown. Voyager 1's navigation depends on tiny hydrazine thrusters, which have been firing delicate pulses for nearly 5 decades to keep the spacecraft properly oriented. These thrusters are among the oldest continuously used pieces of space technology still functioning. In recent years, mission engineers switched to a backup set of attitude control thrusters originally intended for planetary encounters. Surprisingly, these long unused thrusters perform successfully after decades of inactivity, showing the resilience of their design. Each small pulse helps maintain the antenna's alignment with Earth, ensuring that the faint radio signals continue reaching the deep space network. The careful management of these thrusters reflects the patience and precision required to maintain communication across extraordinary distances. Voyager 1's continued ability to orient itself in the darkness of interstellar space stands as a quiet testament to engineering foresight and the enduring reliability of well-crafted machines. Deep space is filled with dust grains, some older than the sun itself, formed in the dying breaths of distant stars. Voyager 1 occasionally detects the presence of these grains indirectly, noting their influence on charged particles and fields. By studying how interstellar dust behaves, scientists gain insight into the life cycle of matter in the galaxy. These grains may later become parts of planets, moons, or comets in new solar systems forming far away. Voyager 1's steady movement through this medium provides a rare opportunity to sample the material between stars. Even though the spacecraft cannot directly analyze many grains, its instruments detect subtle effects that help researchers model how dust flows, collects, and disperses. This gentle interaction with ancient material broadens our understanding of how the universe recycles its building blocks, turning old stars into the seeds of future worlds, all observed by a single distant traveler. Although Voyager 1 no longer sends back images, its earlier discoveries about Jupiter's and Saturn's moons continue influencing modern planetary science. The volcanic activity on Io, revealed in vivid detail by Voyager 1, reshaped understanding of tidal forces and their ability to heat celestial bodies. This discovery helped scientists later predict subsurface oceans on Europa and Enceladus, where tides may keep water liquid beneath icy crusts. Voyager 1's early portraits of these moons remain essential references for comparison with newer missions. Even without visual data now, the spacecraft's legacy continues guiding exploration strategies and shaping theories about habitability beyond Earth. Its long journey shows that knowledge gained early in a mission can echo for decades, influencing research far into the future. Voyager 1's contributions endure quietly, woven into the foundation of planetary science and reminding us that even the oldest data can carry lasting significance. The silence around Voyager 1 is immense, yet that silence carries a sense of peace rather than emptiness. With no planets nearby and no spacecraft to accompany it, Voyager 1 travels alone through regions where nothing disturbs its path. This solitude allows scientists to study undisturbed interstellar conditions, free from the influence of planetary magnetospheres. The spacecraft moves smoothly, unaffected by drag or weather, guided only by gravity and its own momentum. In this calm environment, it continues collecting data that provides a pure view of the galaxy's natural state. For many researchers, Voyager 1 represents a kind of meditative scientific presence, steady, focused, and patiently listening to the universe. Its mission reminds us that exploration does not always require dramatic events. Sometimes the most meaningful discoveries emerge from quiet observation, carried out by a traveler that drifts peacefully through the dark between the stars. Voyager 1 continues to drift through a region where sunlight has grown so faint that it feels more like a distant memory than an active presence. Here, The spacecraft senses the quiet flow of charged particles that move between stars, tracing invisible paths shaped by long-forgotten cosmic events. Every small measurement it beams back to Earth helps researchers understand how interstellar space behaves far from the shelter of the Sun. The spacecraft moves steadily forward, its path shaped only by the gravity of the Milky Way and the momentum it carried from its launch nearly half a century ago. Even though its surroundings seem empty, each reading contributes to a larger picture of the galaxy's structure. Voyager 1's presence in this delicate environment shows how exploration can continue through simple perseverance, with a small machine listening carefully to the faint signals that drift through the quiet reaches of space. Even in the cold darkness of interstellar space, Voyager 1 encounters variations in magnetic fields that tell stories about events happening far beyond the range of human sight. These magnetic fluctuations reveal how charged particles move through the galaxy, shaping the environment that surrounds stars and planets. Scientists analyze these tiny shifts to understand how cosmic weather changes over long distances and long stretches of time. Voyager 1's slow travel gives it a front-row seat to these subtle patterns, offering a calm, uninterrupted view of regions that no other spacecraft has reached. Each small variation it records becomes part of a long timeline that helps researchers compare interstellar conditions with those closer to the Sun. The spacecraft acts like a drifting observatory, steady and unhurried, patiently gathering evidence of the unseen forces that sculpt the galaxy. Its measurements continue to bridge the gap between theory and reality in the stillness of deep space. As Voyager 1 moves deeper into the galaxy, the density of interstellar plasma becomes an important clue for scientists studying how matter behaves outside the Sun's influence. The spacecraft listens to vibrations in the plasma, picking up gentle tones that reveal its density and movement. These signals sound almost like whispers from the void, carrying information about ancient stars that shed their outer layers long ago. Each reading arrives at Earth after traveling for nearly a full day at the speed of light, yet the spacecraft continues sending them faithfully. This careful monitoring allows scientists to build detailed models of how plasma flows through interstellar space, shaping the boundaries around star systems. Voyager 1's persistence in tracking these subtle vibrations provides rare insight into a region that would otherwise remain unknowable. Its quiet observations help humanity understand how the galaxy's most delicate materials drift, interact, and evolve across unimaginable distances. The instruments aboard Voyager 1 were designed to withstand the harsh conditions of space, yet their longevity continues to impress engineers who worked on the mission decades ago. Many of these engineers never expected the spacecraft to operate for so long or travel so far beyond its original route. The fact that the instruments remain functional speaks to the thoughtful design and rigorous testing carried out in the 1970s. Each functioning detector serves as a reminder of the dedication behind the mission, and the spacecraft's ability to send back data after all these years is a quiet triumph of human craftsmanship. Even with limited power, these aging systems continue to operate with a sort of steady patience, allowing the spacecraft to monitor its surroundings without interruption. Their endurance provides scientists with data that could never be gathered by newer missions, simply because no other spacecraft has ventured into such distant territory. As Voyager 1 sends back measurements, the data must be decoded and interpreted by teams on Earth who have grown accustomed to working with extremely weak signals. These signals are so faint that they almost disappear into background noise, yet careful filtering and analysis allow researchers to extract meaningful information. The process requires patience, precision, and an understanding that each bit of data represents an observation made billions of kilometers away. Scientists treat the signals with care, knowing that the spacecraft's ability to transmit such information is limited by its aging systems. This thoughtful approach ensures that nothing is lost or misinterpreted. The collaboration between Voyager 1 and the people who monitor it has become a quiet partnership across vast distances, demonstrating how steady communication can bridge space and time. Every decoded message becomes another piece of the cosmic story that Voyager 1 continues to tell with remarkable dedication. Voyager 1's slow and steady movement through the galaxy gives scientists the rare ability to study changes that occur over decades rather than days or months. Many space missions operate within short timelines, but Voyager 1 provides insights into long-term trends that shape the interstellar environment. These trends include shifts in cosmic rays, variations in plasma density, and subtle patterns in magnetic fields. By comparing measurements taken years apart, researchers can identify changes that would otherwise remain hidden. This long-term perspective helps build a foundation for understanding how star systems evolve and how cosmic materials circulate throughout the galaxy. Voyager 1's ability to contribute to this slow science makes it unique among spacecraft. Its patience, combined with its longevity, allows it to reveal patterns that unfold on timescales much longer than the span of human missions, offering a rare glimpse into the enduring rhythms of the universe. Engineers on Earth continue to adjust Voyager 1 systems with remarkable care, making sure the spacecraft remains functional despite the growing challenges of age and distance. Tiny changes in temperature, fuel levels, and power output require constant monitoring to ensure stable communication. These adjustments reflect decades of accumulated expertise passed down from one team to another. Even though the spacecraft is far beyond the reach of repair, the people guiding it from Earth treat it with the same precision as when it first launched. This ongoing support keeps Voyager 1 healthy enough to send back its scientific observations. The careful stewardship of the spacecraft shows how human dedication can extend the life of a mission far beyond its expected limits. With each successful adjustment, Voyager 1 continues its peaceful drift through interstellar space, maintained by a partnership between engineering skill and the spacecraft's reliable design. As Voyager 1 travels, it carries with it a unique perspective on the boundary between the Sun's influence and the larger galaxy. This perspective allows researchers to refine theories about how star systems interact with the interstellar medium. The spacecraft's measurements help confirm or challenge models that describe the shape of the heliosphere and the forces that define its edge. These insights are important for understanding how cosmic rays reach Earth and how the Sun shields the planets from harmful radiation. Voyager 1's observations contribute to a clearer picture of the environment that future spacecraft, or even distant future travelers, might encounter when venturing beyond the solar system. The data it sends back is like a quiet guidebook to regions no human has ever seen, helping to map a frontier that exists far beyond familiar territory. In this way, the spacecraft continues shaping our understanding of space exploration. Although Voyager 1 has traveled farther than any other spacecraft, it still carries the simple architecture designed decades ago. A main bus, an antenna, and a collection of instruments mounted on booms. This design was crafted for resilience, and its straightforward structure has helped the spacecraft endure the conditions of deep space. Its simple mechanics have proven reliable across enormous distances. The spacecraft's antenna remains its most critical feature, acting as the only link between its remote location and the scientists waiting for its messages. The fact that this structure continues to function despite exposure to radiation, extreme temperatures, and aging materials, is a testament to the thoughtful engineering that went into its creation. Voyager 1's longevity shows that elegant, uncomplicated design can sometimes be more enduring than complex or fragile systems, especially when built to last through decades of isolation in space. The journey of Voyager 1 has inspired countless scientists, students, and explorers who grew up hearing about the spacecraft's achievements. For many, the mission represents the power of curiosity and the value of pursuing knowledge even when the destination is unknown. Schools, museums, and documentaries often use Voyager 1 as a symbol of human exploration, demonstrating how a small spacecraft can change our understanding of the universe. Its story encourages people to imagine what lies beyond the boundaries of current technology and inspires new generations to study astronomy, engineering, and physics. Voyager 1's continued operation keeps its legacy alive, reminding the world that exploration is an ongoing process. Even in the quiet of interstellar space, the spacecraft continues to motivate those who dream of distant stars, proving that inspiration can travel farther than the spacecraft itself. As Voyager 1 drifts farther from the Sun, it experiences a gradual cooling that reflects the extreme temperatures of interstellar space. The spacecraft's systems were designed to withstand such cold, using insulation and waste heat from its power generators to keep critical components warm enough to function. Even as the generators produce less heat over time, engineers carefully manage the spacecraft's configuration to maintain safe temperatures. This delicate balance allows the instruments to continue operating long after the mission's expected end. The harsh cold surrounding Voyager 1 highlights the challenges of operating far from any star, yet the spacecraft's resilience proves that thoughtful thermal design can endure even the most extreme conditions. Its continued function in such an environment shows how engineering foresight can keep a spacecraft alive far beyond the boundaries of the solar system. The path Voyager 1 follows through the galaxy is determined by the gravitational influences it encountered long ago when passing Jupiter and Saturn. Those encounters provided the slingshot effect that sent the spacecraft speeding toward interstellar space. Now, its trajectory is smooth and unchanging, guided primarily by the gravity of the Milky Way itself. This predictable path gives scientists confidence in forecasting its position for thousands of years. Even though the spacecraft will never approach another star closely, its direction helps reveal how the Sun moves relative to the surrounding galaxy. Voyager 1's motion offers clues about the gravitational landscape of the Milky Way, including dense regions, empty pockets, and the overall structure that governs stellar movement. By studying the spacecraft's trajectory, researchers gain insight into the gentle but persistent forces that shape the galaxy's stellar highways. As Voyager 1 continues aging, its power levels gradually decline, forcing the mission team to make careful decisions about which instruments to keep running. These decisions involve predicting which measurements will offer the most scientific value, balancing limited power against the importance of various observations. Each instrument turned off represents a thoughtful choice made to preserve the spacecraft's communication capabilities for as long as possible. This process has transformed the mission into an exercise in prioritization and resourcefulness. Even with reduced functionality, Voyager 1 remains scientifically valuable, providing data no other mission can. The careful management of its power supply reflects the ingenuity of the mission team and the spacecraft's ability to adapt to changing conditions. Its endurance shows how a mission can evolve gracefully, continuing to contribute meaningful observations even in its later years. The signals Voyager 1 receives from the galaxy carry subtle information about the distribution of particles in interstellar space. These particles, though sparse, play an important role in shaping the environment between stars. As the spacecraft moves forward, it helps scientists map variations in particle density, revealing how these materials cluster and disperse across the galaxy. Understanding these patterns helps researchers build models of how star-forming regions develop and how matter circulates throughout the Milky Way. Voyager 1's position in interstellar space makes it uniquely capable of gathering this information. Its slow, steady journey offers a consistent stream of observations that enrich our knowledge of the galaxy's structure. Each reading deepens our understanding of the spaces between stars, enhancing the broader picture of how the universe organizes its most basic building blocks. The vibrations detected by Voyager 1's plasma wave instrument reveal changes in the surrounding environment that often go unnoticed by other sensors. These vibrations occur when charged particles interact with magnetic fields, creating subtle waves that move through space. Scientists analyze these signals to understand how energy travels through the interstellar medium. The data helps explain how disturbances caused by distant supernova or cosmic winds propagate across vast distances. Voyager 1's ability to hear these faint whispers adds another dimension to its exploration, allowing researchers to study phenomena that are invisible to telescopes or particle detectors. These gentle ripples in space form a soundtrack of the galaxy's hidden activity, offering insight into events that occurred long before the spacecraft arrived. Voyager 1 continues listening with patient persistence, translating the quiet motions of interstellar space into valuable scientific information. Even though Voyager 1 is far beyond the planets, it still carries memories of the dramatic encounters that defined its early mission. The images and data it gathered from Jupiter and Saturn remain foundational to modern understandings of gas giants. Researchers still revisit those early observations to compare them with newer missions, finding fresh insights in data collected decades ago. These comparisons reveal how planetary systems evolve over time, showing changes in storms, magnetic fields, and atmospheric patterns. Voyager 1's early work serves as a historical record that continues to inform current science. Its journey demonstrates how the value of exploration extends well beyond immediate discoveries, with data that can shape our understanding for generations. The spacecraft's legacy is a reminder that even brief encounters with distant worlds can leave lasting impressions that guide future exploration. The interstellar space Voyager 1 travels through contains traces of the earliest materials in the universe, remnants forged in the hearts of ancient stars. By studying the particles it encounters, scientists gain clues about the processes that created elements long before the sun formed. These materials eventually contribute to new stars and planets, forming a cosmic cycle of creation and renewal. Voyager 1's ability to sample these ancient remnants provides rare insight into the galaxy's history. Although the spacecraft cannot directly analyze the particles, its instruments detect their presence and influence, allowing researchers to infer their properties. This quiet interaction with cosmic history shows how even a distant spacecraft can deepen our understanding of the universe's origins. Voyager 1 becomes a messenger from a time long before humanity existed, carrying stories written in the oldest materials drifting through the galaxy. The isolation of Voyager 1 in deep space highlights its unique role as a lone observer of regions untouched by human presence. Unlike spacecraft orbiting planets, which are influenced by local environments, Voyager 1 experiences the pure conditions of interstellar space, This solitude allows it to record data without interference from planetary magnetospheres, atmospheres, or radiation belts. Its position gives scientists a clean view of how the galaxy behaves in its quietest moments. The spacecraft's independent journey emphasizes the vastness of space, where even the most advanced machines become tiny travelers navigating immense distances. Voyager 1's solitude is not desolate but peaceful, offering clarity and perspective on the universe's true scale. Its measurements remind us that exploration often takes place far from familiar surroundings, in quiet places, where patience and persistence reveal the hidden nature of reality. Voyager 1's long journey gives scientists the rare chance to study how cosmic rays behave far from the sun's protective influence. Close to Earth, these high-energy particles are partially blocked or shaped by the heliosphere, but out in interstellar space they move freely, revealing their true nature. Voyager 1 detects their changes in intensity, direction, and energy, helping researchers understand where these particles come from and how they travel across the galaxy. Some cosmic rays may have been launched by supernova explosions that happened millions of years ago, their energy carrying ancient stories through the cosmos. As Voyager 1 drifts farther from the heliosphere's shielding, these particles grow stronger and more varied, painting a clearer picture of the galaxy's energetic background. This data deepens scientists' understanding of cosmic radiation and helps refine models that describe how high-energy particles shape planetary environments and influence the formation of stars. The spacecraft's distance from the Sun allows it to observe the true nature of the local interstellar magnetic field, unfiltered by the Sun's influence. This magnetic structure plays a critical role in shaping the movement of cosmic particles and the flow of interstellar plasma. By measuring how the magnetic field twists, shifts, and pulses, Voyager 1 helps researchers understand the architecture of the galaxy's magnetic backbone. These observations reveal how magnetic pressure balances against particle pressure, creating delicate equilibrium at the edge of the heliosphere. Scientists use the spacecraft's data to refine theories about how star systems interact with the galaxy around them. Voyager 1's slow drift through these regions offers a continuous record of conditions that would otherwise remain hidden. Its measurements serve as a compass, pointing toward a deeper understanding of how invisible forces help organize the Milky Way's structure. As Voyager 1 moves farther away, its radio signal becomes increasingly faint, stretching the limits of the Deep Space Network's detection capabilities. Engineers must carefully tune massive antennas to catch the spacecraft's whispers from billions of kilometers away. These antennas, spread across multiple continents, work together to keep the signal alive as Earth rotates. Their precision and timing allow them to gather weak transmissions that would otherwise vanish into cosmic noise. Voyager 1's continued communication is a triumph of both engineering and determination, showing how human ingenuity can maintain contact with a spacecraft long past its expected lifetime. Each faint message serves as a reminder of the connection between Earth and this distant explorer, demonstrating how careful coordination and advanced technology can bridge distances that seem impossible to cross. The collaboration between spacecraft and ground stations keeps Voyager 1's voice alive. Because Voyager 1 is now far beyond the Sun's influence, its measurements provide a baseline for understanding what space is like where no star dominates. This baseline helps researchers compare interstellar conditions near our solar system with conditions near other stars. By studying how plasma density, particle flow, and magnetic fields behave in this quiet region, scientists can estimate what distant star systems might look like at their edges. These insights are valuable for understanding exoplanet environments and how young stars shape their surroundings. Voyager 1's quiet journey thus contributes to the broader study of star formation and galactic evolution. Even though the spacecraft is small and aging, its position outside the heliosphere gives it a powerful scientific vantage point. Its continued measurements serve as a guide to understanding space conditions around other stars across the galaxy. The spacecraft's hydrazine fuel, used for controlling its orientation, is nearly depleted after decades of use. Engineers must carefully manage the remaining fuel to ensure that Voyager 1 keeps its antenna pointed toward Earth. This delicate balancing act requires precise planning, since even tiny adjustments use precious fuel that cannot be replaced. Despite these constraints, the spacecraft continues to operate with remarkable stability. Each small pulse from its thrusters reflects the careful work of mission controllers who monitor its orientation. The dwindling fuel highlights the spacecraft's age, but also underscores its endurance. Even with limited resources, Voyager 1 maintains steady communication and continues its scientific mission. The remaining fuel is expected to last only a few more years, but until then, the spacecraft remains a reliable observer of interstellar space. Even though Voyager 1 no longer carries a functioning camera, its earlier images still shape how we visualize the outer planets. These photographs captured Jupiter's colorful storms, Saturn's delicate rings, and the rugged surfaces of their moons with unprecedented clarity. Scientists continue using these images to compare changes observed by newer missions. The detailed views provided by Voyager 1 helped inspire future explorations, such as Cassini's study of Saturn and Juno's investigation of Jupiter. While the spacecraft now travels through darkness with its camera silent, the legacy of its early images remains alive in scientific literature, classrooms, and documentaries. They continue to offer perspective on the beauty and complexity of our solar system. Even without new pictures, Voyager 1's visual legacy continues to inspire curiosity and wonder about the worlds it once visited. Voyager 1's continued journey shows the value of long-duration missions. While most spacecraft operate for a decade or less, Voyager 1 has remained active for nearly half a century. This extraordinary longevity provides scientists with an extended timeline of observations, enabling studies impossible with shorter missions. Its data reveals how space conditions evolve over decades and how the sun's influence changes as it moves through the Milky Way. The spacecraft's endurance demonstrates that missions built with durability and adaptability can contribute scientific insights long after their original goals are met. Voyager 1 has transitioned from planetary exploration to interstellar research, proving that missions can evolve as they age. Its longevity inspires future mission planners to consider how spacecraft might operate far beyond their original designs, extending humanity's reach deeper into the cosmos. As Voyager 1 drifts through interstellar space, it encounters a region where the particles are ancient, remnants of long-dead stars. These particles include atoms of hydrogen and helium formed shortly after the Big Bang, along with heavier elements forged in supernova explosions. The spacecraft's instruments detect shifts in particle density and energy that help researchers understand how these materials travel and mix across the galaxy. This understanding is crucial for piecing together the life cycle of matter in the universe. Voyager 1's position allows it to study these ancient materials firsthand, providing insight into the cosmic environment that eventually gave birth to our solar system. The spacecraft's steady observations bring clarity to questions about how elements spread and combine to form new stars, planets, and potentially life itself. Its role as a quiet witness to the galaxy's ancient materials deepens our knowledge of cosmic history. The spacecraft's radioisotope generators create both power and heat, helping keep Voyager 1's systems warm enough to function. As the plutonium inside them decays, the heat output decreases, making temperature management more challenging. Engineers must adjust the spacecraft's configuration to keep vital components above freezing. This careful thermal management is essential in interstellar space, where temperatures are near absolute zero. The spacecraft's ability to maintain adequate warmth despite declining power demonstrates the effectiveness of its insulation and design. These generators were originally expected to last only a few decades, yet they continue powering Voyager 1's journey. Their slow decline adds a sense of poignancy to the mission, as each year brings new challenges. Even so, the spacecraft continues working with quiet determination, proving how thoughtful engineering can withstand the harshest environments in the universe. Voyager 1's early discoveries about Jupiter's moons introduced the idea that many celestial bodies might be more dynamic than previously believed. The volcanic plumes on Io showed that tidal forces can generate enough heat to melt rock, while the cracked ice of Europa suggested the possibility of a subsurface ocean. These findings reshaped scientists' understanding of planetary geology and expanded the search for potentially habitable environments beyond Earth. Even though Voyager 1 no longer studies planets, its early observations remain deeply influential. Research into ocean worlds and icy moons continues today, guided in part by the groundbreaking discoveries the spacecraft made decades ago. Its early contributions serve as a reminder that even brief flybys can produce insights that transform entire fields of study. Voyager 1's legacy in planetary exploration continues to grow, shaping missions that search for life elsewhere in the solar system. The spacecraft's steady movement through interstellar space allows scientists to study how the sun's influence fades gradually over distance. Close to the sun, the solar wind dominates, shaping the environment around planets. Farther out, this influence weakens until it merges with the galactic background. Voyager 1's journey across this boundary helped confirm theories about the heliopause and revealed that the transition is more complex than originally thought. The spacecraft recorded sudden shifts in particle density, magnetic field alignment, and plasma environment that indicated the edge of the heliosphere is not a simple barrier, but a dynamic region shaped by competing forces. These observations refine our understanding of how stars interact with their surroundings and how solar systems remain connected to the galaxies they inhabit. Although Voyager 1 moves through a region that seems empty, the interstellar medium is filled with faint traces of dust, plasma, and cosmic radiation. These materials are spread so thinly that a cubic meter of interstellar space contains only a handful of particles, yet they hold clues to cosmic processes that shape galaxies. Voyager 1's ability to detect these tiny traces allows scientists to understand how they behave over immense distances. Its observations reveal how dust aligns with magnetic fields, how plasma waves travel, and how cosmic rays scatter. These discoveries help researchers build models of galactic evolution, showing how even the quietest regions play important roles in shaping the universe. The spacecraft's presence in this delicate environment demonstrates how exploration often involves listening to the faintest signals rather than observing dramatic events. Voyager 1's long voyage allows researchers to study how radiation levels change depending on the spacecraft's distance from the sun. As it moved farther from the protective influence of the heliosphere, cosmic radiation levels increased significantly. Scientists monitor these changes to understand how radiation behaves in different environments, and to predict what future spacecraft might encounter on interstellar missions. This information is crucial for designing spacecraft that can withstand long-term exposure to cosmic rays. Voyager 1's radiation measurements offer a unique perspective on the galactic environment, providing a window into the unseen forces that shape the universe. Even though the spacecraft lacks modern shielding, its instruments continue to record valuable data that helps researchers understand the challenges of deep space travel. Voyager 1's crossing of the heliopause is one of the most significant achievements in the history of space exploration. This moment marked humanity's first step into interstellar space, confirming theories that had been discussed for decades. The spacecraft's instruments recorded the transition through a combination of rising plasma density, changing particle flow, and shifts in magnetic field direction. These signatures provided definitive evidence that Voyager 1 had left the Sun's protective bubble and entered the broader galaxy. The crossing was not dramatic. It happened quietly, with data slowly reaching Earth over many hours. Yet its significance is profound, representing the moment when a human-made object permanently left the solar system. This milestone symbolizes our ongoing effort to explore beyond familiar boundaries. Because Voyager 1 continued transmitting long after its expected end, it became a symbol of endurance and commitment in scientific communities worldwide. Students often learn about the mission as an example of how careful engineering and thoughtful planning can create technology that lasts far beyond expectations. The spacecraft's long lifespan encourages young scientists to pursue missions that prioritize durability and long-term value. Voyager 1's story shows that exploration is not always about rapid breakthroughs. Sometimes it is about slow, continuous learning. The spacecraft's endurance reflects a belief in patient discovery, where each small observation contributes to a larger understanding. This mindset influences new missions designed to explore the outer solar system and beyond. The spacecraft's design included redundancy in key systems, allowing it to survive damage or failures that might otherwise have ended the mission early. Redundant circuits, backup thrusters, and duplicate pathways helped ensure that Voyager 1 could continue functioning even if something broke. Over the years, some systems have indeed failed, but the spacecraft's redundant features allowed it to adapt and keep operating. This resilience highlights the value of building spacecraft with multiple layers of protection, especially for missions expected to encounter unknown conditions. Voyager 1's long life is partly due to this thoughtful design approach, which allowed it to overcome technical challenges that would have ended less robust missions. As Voyager 1 moves through regions untouched by sunlight, it encounters particles that have been traveling undisturbed for millions of years. These particles carry information about distant supernova explosions, stellar winds, and the broader galactic structure. By detecting how these particles interact with magnetic fields, the spacecraft helps researchers understand how energy moves through the galaxy. These insights are essential for understanding how stars influence their surroundings and how cosmic environments evolve. Voyager 1's data builds a bridge between human science and the ancient forces shaping the universe, offering a unique perspective on the galaxy's hidden processes. Voyager 1's enormous distance from Earth allows it to act as a natural probe of how the solar system moves through the galaxy. As the Sun orbits the center of the Milky Way, it travels through regions with slightly different densities, magnetic fields, and particle concentrations. Voyager 1's measurements help reveal how these changes affect the heliosphere and how the boundary of the Sun's influence shifts over time. By studying these variations, scientists gain insights into the relationship between our solar system and the larger galactic environment it passes through. These findings help refine models of galactic weather and star system interactions, offering a clearer understanding of how the Sun navigates its path through space. Voyager 1, drifting silently far ahead of the planets, continues to send back clues that help researchers trace the solar system's broader journey across the Milky Way's vast and ever-changing landscape. Interstellar space is not completely uniform, and Voyager 1's gradual movement through it allows scientists to observe small regional differences that shape the galactic environment. These variations include subtle shifts in plasma density, changes in magnetic field direction, and fluctuations in cosmic ray intensity. Such patterns reveal how clouds of interstellar material drift, stretch, compress, and evolve over long periods. Voyager 1's steady observations help researchers identify transitions between these regions, giving a clearer picture of the large-scale structure of the galaxy. These findings are important for understanding how star-forming regions develop and how interstellar clouds influence the birth of new solar systems. The spacecraft's position, far outside the Sun's direct influence, makes it uniquely suited to study these delicate boundaries, allowing scientists to map the unseen textures of space that lie between the stars. Voyager 1's ability to transmit data across extreme distances highlights the incredible power of radio communication. Even though the spacecraft sends signals with less power than a typical refrigerator light bulb, the Deep Space Network catches these faint transmissions using massive antennas tuned with extraordinary precision. This technological achievement demonstrates how advanced engineering can overcome seemingly impossible challenges. The continuing success of these communications shows humanity's ability to maintain contact with machines, traveling far beyond any possibility of repair. Each message received reinforces the connection between Earth and the spacecraft, proving that even across billions of kilometers, communication remains possible through persistence and innovation. Voyager 1's faint signals are a reminder that exploration relies not only on spacecraft, but also on the ingenuity of the people and systems supporting it from home. The spacecraft's gradual movement away from the Sun has helped confirm theories about how far the solar wind extends before merging into the interstellar medium. Scientists long debated the size and shape of the heliosphere, predicting the boundary but lacking direct data. Voyager 1's crossing provided proof of the heliopause location and showed that the transition is complex, involving sudden jumps in particle density and shifts in magnetic alignment. These observations revealed that the heliosphere is not a simple bubble, but a dynamic, irregular region shaped by both solar and galactic forces. The spacecraft's journey continues to refine this understanding, offering new clues as it travels deeper into interstellar space. These insights help build a more accurate picture of how star systems interact with their surroundings and how cosmic boundaries form and evolve. Even though Voyager 1 cannot capture images anymore, it still carries memories of the planetary flybys that shaped its mission. The spacecraft's encounters with Jupiter and Saturn created a foundation for understanding gas giant atmospheres, ring systems, and volcanic moons. These early discoveries continue influencing modern missions, which build upon insights the spacecraft gathered decades ago. Scientists often return to Voyager 1's early data to compare changes over time, tracking shifts in storms, ring structures, and magnetic fields. This comparison helps reveal long-term trends that only missions with extended timelines can detect. Voyager 1's early work remains relevant, demonstrating that even in its silence, the spacecraft continues contributing to scientific progress. Its photographs and measurements serve as a time capsule of an era when humanity first explored the outer planets up close. The interstellar medium contains charged particles that interact with magnetic fields to create ripples of energy that move through space. Voyager 1's plasma wave instrument detects these faint ripples, turning them into signals that scientists can study. These signals provide clues about particle density and how energy flows across regions untouched by stars. By listening to these gentle vibrations, researchers gain insight into the invisible structures that shape the galaxy. The data helps explain how shock waves from ancient supernovae travel across enormous distances and influence the environment between stars. Voyager 1's unique ability to detect these subtle waves makes it an invaluable tool for understanding deep space processes. Its patient listening reveals a hidden soundtrack of the galaxy, composed of quiet movements and ancient echoes carried through the interstellar medium. Voyager 1's location beyond the heliopause allows it to study the influence of galactic cosmic rays without interference from the Sun. These high-energy particles originate from distant supernova explosions and other energetic cosmic events. By observing changes in their intensity and composition, Voyager 1 provides insight into how cosmic rays move through the galaxy and how they affect planetary atmospheres. This information helps researchers understand radiation environments around other stars and contributes to planning for future interstellar missions. The spacecraft's steady observations offer a rare window into the energetic processes that shape galaxies. Even as its power declines, Voyager 1 continues delivering important data that expands our knowledge of the universe's most energetic particles. Voyager 1 travels through a region where the relative motion of the Sun and interstellar medium creates a complex interplay of particles and magnetic fields. This interaction forms a kind of wake behind the Sun as it moves through the galaxy. Voyager 1's instruments detect how this wake affects particle movements and how magnetic fields twist and stretch in response. These observations help researchers understand how stars interact with their surrounding environment, shaping the space through which they move. The spacecraft's position allows it to observe these interactions firsthand, providing valuable data about the nature of stellar motion. Understanding this interplay is important for modeling how other star systems behave as they travel through the galaxy. Voyager 1's observations continue to guide scientists in refining these complex models. The spacecraft's limited power supply requires careful prioritization of which instruments remain active. Engineers must decide which scientific goals are most important at each stage of the mission. As power levels decline, these decisions become more challenging. Despite these limitations, the remaining instruments continue to provide valuable data that no other mission can offer. The process of choosing which instruments to keep running reflects the evolving goals of the mission, balancing the need for communication with the desire to gather as much scientific information as possible. This careful management ensures that Voyager 1 continues contributing to scientific discovery, even as its capabilities diminish. Its endurance demonstrates the importance of thoughtful planning and adaptability in long-duration missions. Voyager 1's slow drift allows scientists to study how interstellar space changes over long periods. Unlike missions that rapidly pass through regions of interest, Voyager 1 moves at a pace that reveals gradual shifts in particle density, magnetic fields, and cosmic ray flow. These slow changes help researchers understand long-term processes that shape the galaxy. By comparing data collected years apart, scientists can identify patterns that stretch across time, offering insights into how the interstellar medium evolves. Voyager 1's patient movement through space makes it a unique observer of these long-term trends, providing a steady stream of information that complements data from faster missions. Its role as a long-term observer helps deepen our understanding of the galaxy's slow, quiet transformations. The extreme distance between Voyager 1 and Earth requires the spacecraft to maintain precise antenna alignment for communication. Tiny deviations could cause its signal to miss Earth entirely. Mission controllers use limited fuel and occasional thruster pulses to correct its orientation, ensuring the antenna stays pointed at our planet. This ongoing effort represents a delicate balance between conserving fuel and maintaining reliable communication. The success of this alignment over decades highlights the skill of the engineers involved and the spacecraft's remarkable stability. Even small adjustments require careful planning due to the spacecraft's fragile resources. Voyager 1's continued ability to send data across billions of kilometers reflects a long-standing partnership between precise engineering and thoughtful mission operations. Voyager 1's flight through the galaxy provides a rare opportunity to measure how interstellar space varies in different directions. The spacecraft's trajectory takes it slightly above the plane of the solar system, offering a perspective that complements models of the galaxy's broader structure. Its observations help researchers understand how interstellar material is distributed across different latitudes of the Milky Way. This information is valuable for refining theories about galactic formation and evolution. Even though the spacecraft is only sampling a narrow path through space, its data helps construct a more complete picture of the galaxy's diverse environments. Voyager 1 acts like a single, slow-moving probe, stitching together a map of the interstellar medium from one unique vantage point. The spacecraft's interactions with interstellar dust, though indirect, provide clues about the composition and behavior of the galaxy's smallest particles. These grains are remnants of older stars and play a critical role in forming planets and new solar systems. Voyager 1's measurements of particle impacts, plasma behavior, and magnetic field changes help researchers infer how dust moves and how it affects the environment around it. These insights are crucial for understanding the initial conditions of planetary formation. Voyager 1's journey through these delicate regions offers a rare chance to observe the earliest building blocks of cosmic structures, revealing how they drift and evolve over time. The mission's longevity has turned Voyager 1 into more than just a spacecraft. It has become a symbol of persistence, curiosity, and peaceful exploration. People around the world follow its journey with a sense of wonder, imagining what it encounters in the quiet reaches of space. Its steady progress inspires artists, writers, scientists, and students, reinforcing the idea that exploration is a universal human desire. The spacecraft's survival against the odds encourages a broader appreciation for missions that value endurance over speed. Voyager 1 represents a journey that continues not through haste, but through quiet determination and resilience, offering a reflection of humanity's own long search for understanding. As Voyager 1 moves deeper into interstellar space, it travels through regions shaped by ancient supernova remnants. The shockwaves from these long-ago explosions influence the density and motion of particles throughout the galaxy. By measuring changes in particle flow and magnetic field direction, Voyager 1 helps scientists map the lingering effects of these cosmic events. These findings reveal how supernovae shape the environment in which new stars and planets form. Voyager 1's ability to detect these ancient influences highlights the spacecraft's unique position as a witness to galactic history, offering insights into events that occurred long before the solar system existed. The spacecraft's ancient instruments continue performing tasks that once depended on cutting-edge technology. Although modern sensors are far more advanced, Voyager 1's older instruments remain uniquely valuable because they operate in a region no newer mission has reached. Their continued functionality proves the durability of simple, well-designed systems. These aging devices provide a steady flow of data that deepens our understanding of interstellar space. Even without the precision of modern technology, they remain reliable tools for studying the galaxy's quiet regions. Their persistence shows how well-crafted engineering can withstand decades of cosmic exposure. Voyager 1's presence in interstellar space provides a rare baseline for comparing conditions across different solar systems. By understanding what space is like far from the Sun, scientists can better interpret observations from distant stars, helping create models that describe how stellar winds and magnetic fields shape their environments. This baseline influences studies of exoplanets, star formation, and the behavior of cosmic radiation. Voyager 1's quiet journey contributes to understanding the universality of these processes, connecting our solar system's behavior with those around other stars. Voyager 1's continued movement into deeper interstellar space lets scientists observe how the density of plasma changes as it drifts farther from the Sun's influence. These shifts reveal how interstellar material is distributed in subtle waves shaped by the remnants of ancient stars. By recording how plasma vibrations differ across regions, the spacecraft helps researchers understand the composition and motion of the interstellar medium. These observations give insight into how galactic environments vary on scales too large to study from within the solar system. Voyager 1's distance allows it to detect gradual changes that unfold over decades, offering a long-term view of how plasma behaves far from any star. Its steady monitoring of these faint vibrations provides evidence that the galaxy is filled with delicate transitions rather than empty space, deepening our understanding of the quiet but intricate structures that stretch between stars. Despite its age, Voyager 1 continues to detect changes in cosmic ray intensity as it travels farther from the heliosphere. These fluctuations provide evidence that the flow of high-energy particles is influenced by both local and large-scale galactic forces. By observing how these particles increase or decrease across different regions, scientists gain insight into how cosmic rays propagate through the Milky Way. This information improves models used to predict radiation environments near other stars. The spacecraft's ability to detect these variations makes it a valuable tool for studying galactic processes that occur across vast distances. Even though the patterns are subtle, each shift in particle intensity contributes to a deeper understanding of the galaxy's energetic landscape. Voyager 1's steady observations remind us that progress in science often comes from patient listening rather than dramatic moments. As Voyager 1 travels on its silent path, the golden record remains one of the most poetic parts of its mission. While the spacecraft no longer encounters planets or moons, this small artifact continues to symbolize humanity's hope for connection across cosmic distances. The record carries music, greetings, and images representing the diversity of life on Earth. It reflects the optimism of those who created it, imagining that long after humanity is gone, Voyager 1 may still drift through the galaxy, carrying a message of goodwill. Although the likelihood of the record being discovered is extremely small, its presence adds a layer of meaning to the spacecraft's journey. It reminds us that exploration is not only about scientific data, but also about expressing curiosity, kindness, and imagination. Voyager 1 carries this message quietly, a gentle echo of humanity traveling through the dark. Voyager 1's increasing distance from Earth means that the time it takes for signals to reach home grows longer each year. Currently, each transmission takes more than 22 hours to travel one way at the speed of light. This delay means that engineers must plan commands with great care, anticipating conditions far in advance. The long time lag gives the mission a feeling of deep patience, as every instruction requires almost 2 days to confirm. Despite the immense distance, communication remains steady, showing the remarkable precision of both the spacecraft and Earth's receiving systems. This slow exchange reflects the nature of Voyager 1's mission: quiet, deliberate, and persistent. It also serves as a reminder of how far human technology has reached, extending our presence into regions of the galaxy where sunlight is little more than a memory. The spacecraft's path will take it near no significant stars for tens of thousands of years, yet it continues moving confidently into the unknown. Its trajectory carries it toward the general direction of the constellation Ophiuchus, though by the time it reaches that region, the stars themselves will have shifted. This long journey reflects the difference between human time and cosmic time, where distances and durations stretch beyond comprehension. Voyager 1's continued travel emphasizes the vastness of the Milky Way and the enormity of space between stars. Even though it is unlikely to encounter another planetary system, its presence in the galaxy remains significant. It represents the first step in humanity's expansion into interstellar space, a quiet pioneer carrying knowledge, messages, and scientific instruments far beyond the solar system's boundary. Over the decades, scientists have relied on Voyager 1 to confirm theoretical predictions about interstellar conditions. Many models about plasma density, magnetic fields, and cosmic rays were developed long before the spacecraft reached these regions. Voyager 1's data has allowed researchers to test these theories in real environments, correcting mistakes, refining assumptions, and validating ideas that were once speculative. The spacecraft's readings act as a bridge between theory and observation, guiding scientific progress with direct measurements. This partnership between predictions and real data shows how patient exploration strengthens scientific understanding. Voyager 1 continues, contributing to this process as it travels farther, offering fresh evidence from regions where no spacecraft has gone before. Its role in shaping scientific theory demonstrates the lasting value of long-term missions. The spacecraft's instruments, though simple by today's standards, continue to detect subtle patterns that reveal the structure of the interstellar medium. These patterns include small fluctuations in magnetic fields, gentle gradients in plasma density, and faint whispers of energy moving through space. Together, these signatures help scientists visualize the invisible environment that surrounds stars across the galaxy. Voyager 1's steady measurements create a mosaic of interstellar space, piece by piece, showing that the galaxy is far from empty. The spacecraft's long journey provides context that short missions cannot achieve, allowing researchers to track trends that unfold over decades. Even as its instruments age, they remain sensitive enough to detect these faint signals, continuing to expand our map of the Milky Way's hidden structures. There is a calm beauty in the idea that Voyager 1 is now drifting through regions shaped by stars that lived and died long before humanity existed. The particles surrounding the spacecraft were forged in distant supernova explosions, cooling over millions of years and spreading throughout the galaxy. These ancient materials will one day contribute to new stars and planets, continuing the cycle of cosmic renewal. Voyager 1's presence in this environment allows humanity to listen to the oldest stories written in the galaxy's dust and plasma. By recording how these ancient materials behave, the spacecraft helps scientists understand the long-term processes that shape galactic evolution. Its journey serves as a reminder that everything in the universe is connected through cycles of creation and transformation. The mission's longevity has allowed multiple generations of scientists to work with Voyager 1, creating a unique continuity across time. Researchers who began their careers during the spacecraft's planetary encounters now mentor younger scientists analyzing its interstellar data. This passing of knowledge reflects the mission's endurance and the shared commitment to exploration. Voyager 1 has become more than a machine. It is a scientific legacy that spans decades, linking people through curiosity and discovery. This continuity highlights how long-term missions enrich the scientific community, offering opportunities for collaboration and mentorship that extend across generations. Voyager 1's ongoing operation symbolizes the endurance of human inquiry, carried forward by the people who study its quiet signals. The spacecraft's increasingly weak power supply requires careful planning to preserve its most essential systems. Engineers must decide which components to shut down, ensuring that key instruments remain functional for as long as possible. This slow reduction in capabilities mirrors the natural aging of the spacecraft and adds a reflective quality to the mission. Even as some systems fall silent, Voyager 1 continues to operate with resilience, maintaining its connection to Earth. The gradual fading of its power is a reminder that every journey has limits, yet the spacecraft's endurance remains impressive. With careful management, it continues sending valuable data, proving that even limited resources can produce meaningful results. Voyager 1's position allows it to detect interactions between interstellar material and the trailing edge of the heliosphere. Although it has crossed the boundary, remnants of solar influence extend outward, creating overlapping regions where galactic and solar particles mix. Voyager 1's sensors record how these interactions evolve over time, offering clues about how star systems blend into the surrounding galaxy. These observations help refine models of how heliospheres form and how they respond to external forces. The spacecraft's continued presence near this transitional zone provides valuable insight into the delicate dynamics of cosmic boundaries. The timeless silence around Voyager 1 makes it one of the most serene places in the universe. With no planets nearby, no sunlight to illuminate its surroundings, and no other spacecraft to disturb its path, Voyager 1 moves through a region defined by stillness. This quiet environment emphasizes the peaceful nature of interstellar space, where events occur on scales too slow for human senses to perceive. The spacecraft's calm surroundings allow its instruments to detect faint signals without interference, creating a clean record of interstellar conditions. Its solitary journey highlights the gentle side of exploration, where discovery comes not from dramatic encounters, but from quiet observation and steady movement through the vast cosmic night. As Voyager 1 continues outward, it helps clarify the structure of the local interstellar cloud, a region of space through which our solar system is currently moving. By measuring the density and magnetic properties of the interstellar medium, the spacecraft contributes to models describing this cloud's shape and behavior. These findings help scientists understand how the Sun interacts with neighboring regions of the galaxy and how interstellar clouds influence the heliosphere. Voyager 1's data enriches our knowledge of the Sun's surroundings, revealing that even the space between stars has complex structures worth studying. Even though Voyager 1 will eventually fall silent, its trajectory ensures that it will continue traveling through the galaxy for millions of years. Long after its instruments stop working, the spacecraft will drift past distant stars, carrying with it the golden record and the legacy of human curiosity. Its long future represents a quiet continuity that extends far beyond humanity's current moment. The idea that a human-made object will continue moving through the Milky Way long after civilization changes adds a profound sense of perspective. Voyager 1 becomes a symbol of endurance, not only in science, but in existence itself. Voyager 1's operations team has adapted to unexpected challenges over the years, finding creative solutions to problems that arise from the spacecraft's age and distance. These solutions often involve reprogramming old systems, rerouting power, or reviving instruments that have been dormant for decades. This adaptability demonstrates the ingenuity required to maintain a mission so far beyond its original scope. The ongoing effort reflects a pursuit of knowledge that continues despite obstacles. Each successful adjustment extends the life of the mission and deepens our connection to the distant spacecraft. The spacecraft's precise trajectory allows astronomers to verify models of the Sun's gravitational influence. By tracking Voyager 1's movement over long periods, scientists confirm predictions about how gravity shapes the paths of objects leaving the solar system. These measurements also help refine calculations about the Sun's mass distribution. Even though the spacecraft is far beyond the planets, its motion still carries the subtle imprint of the Sun's gravity, creating an elegant demonstration of celestial mechanics. Voyager 1's long voyage highlights the stability of the Milky Way's gravitational field on large scales. As the spacecraft travels through the galaxy, its path remains steady, shaped by forces that remain consistent across vast distances. This stability allows scientists to predict its future motion with remarkable accuracy. The spacecraft's smooth trajectory provides insight into the structure of the galaxy and the gravitational environment that governs stellar motion. Its journey becomes a practical example of the large-scale harmony that defines the Milky Way. The spacecraft's onboard computer system, though limited by modern standards, remains a triumph of reliability. Its memory and processing power are tiny compared to modern devices, yet it continues to execute commands, store data, and manage essential functions. This simple computer was built for durability, designed to survive radiation, cold, and isolation. Its continued operation reflects the strength of straightforward, efficient engineering. Even as its capabilities fade, the computer remains a testament to the enduring value of robust design. Voyager 1's influence extends beyond science, inspiring art, literature, and music. Creators around the world have imagined stories about its journey, turning its path into a symbol of solitude, hope, and timeless exploration. The spacecraft's mission resonates with people because it represents the universal desire to reach beyond known horizons. Its quiet persistence encourages reflection on humanity's place in the cosmos and the meaning of exploration. Through these creative expressions, Voyager 1 continues traveling, not only through space but through culture, imagination, and human emotion. As we reach the end of this quiet journey, take a moment to imagine Voyager 1 still drifting in the dark, farther from home than anything we've ever made. Out there, beyond the sun's warm reach, it keeps sending its gentle whispers back to us, reminding us that curiosity doesn't stop at the edge of the solar system. Its tiny signal, crossing billions of kilometers, shows how far a single spark of human imagination can travel. And as you rest tonight, let the thought settle softly around you. Somewhere in the deep calm of interstellar space, a small spacecraft carries our stories, our questions, and our hope into the endless night. May its steady journey guide you into a peaceful dream of stars, distance, and quiet wonder. Good night and sweet dream.